The video for section 9.5 deals with the natural logarithm and the natural exponential. So, the natural logarithm is based off of the number e. Now, e is based off of, it is a constant, but it is a constant with no repetition and no end in the decimal. And it is on your calculator here if you wanted to look there. There are two places that it shows up. One, it shows up as the actual number if you hit second, and that it'll show up as the actual number, which is approximately 2.718281828. And it does seem like it repeats, but if you add extra decimal places here, it'll start changing. And then also we have the exponential function here, which is e to the x, so you can plug in any variable. If you use e as a base, you can raise it to any number. If we wanted to find, for instance, e to the 1, which is just e, we would put that in and we get that same number. So again, this is approximately 2.718, and what this stands for is 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 plus 1 over 1 times 2 times 3 times 4 off forever if you were to add all of these fractions together is what you would get 2.718. So this is the natural exponential, and based off of that we have a natural logarithm. So this would be the logarithm base e of a function, and we have a shorthand notation for it, which is simply ln of x, sometimes written ln of x. And again, this is also on your calculator. It is right here, it is that button ln, and again, if you were trying to find a specific number, then you would plug it into your calculator as such. So, a few examples here. If we want to find e squared, we simply, again, you've got the option of either going e to the x, and then you can put that exponent 2 in, and you get 7.39 essentially. And now I want you to take a second here. This should be actually a negative exponent, negative 1.2. I want you to pause the video here and find e to the 6th and e to the negative 1.2. So if you plug these into the calculator, you should have found that e to the 6th was 403.4, and that e to the negative 1.2, this is going to get smaller because it's a negative exponent, would be 0.301. Likewise, we can also take the natural logarithm of numbers in our calculator. All we have to do is hit the ln button, and then we plug in our number 4, close the parentheses, and we find that the natural log of 4 is 1.39. So again, I want you to pause the video here, make sure you're okay with the calculator, find the natural log of 327 and the natural log of e. So you should have found that the natural log of 327 was 5.79, and that the natural log of e was 1, and this makes sense. Again, natural log is log base e. If you're taking that of the base itself, e, the exponent in this case is 1, so the natural log of e is equal to 1. We can also use this information to solve logarithmic and exponential equations. For instance, if we have the natural log of x and we want to find essentially what e to the 0.475 is, that's going to be our x. We have options. We can either rewrite it in the form, which would be e to the 0.475 is equal to x. And if you plug that into your calculator, we end up with, so if you have e to the 0.475, close parentheses, end up with 1.61. So x in this case is 1.61, and that would be how we would solve this equation. Another way to look at this is to say, okay, well, to get rid of natural log, the inverse function would be to take e raised to that and e raised to both sides. So again, e and natural log are inverse functions, so they leave what's inside x, and you end up with e to the negative 3.77. So this is essentially the same thing we did before, it's just the sides of the equation are flipped. So again, if we plug this into the calculator, we've got e to the negative 3.77, and we get 0.0231. So again, that makes sense. E to a negative exponent is going to give us a smaller number decimal, and in this case it's 0.0231. Now we can use this function in application, and one such application is continually compounded growth. And typically this is referred to as whatever your principal amount is, so y is equal to whatever your principal amount is, and then e raised to your rate times the amount of time. So some people think of this as, remember this as PERT. Again, P is your principal or initial amount, E is your function, R is your rate, and T is time. So again, this is rate per time. So suppose Sarah invests $3,500 at 8.25% compounded continuously. So this is what continuously compounded growth does. How much money will she have in the account after 6 years? So if we plug this into our equation, we have y is equal to our principal, our initial amount is 3,500. We multiply that by e to the r. Again, we need to make sure we write it in decimal form. 0.0825 would be 8.25%, because this would be 8.25%. Move the decimal place 2 places. And then our time here is 6 years. So again, if we go to our calculator, we take 3,500 times e to the 0.0825 times 6. And we end up with, after 6 years, she will have $5,741.74. Okay, so this would be how much you would earn continuously if it's compounded continuously over 6 years. A few more examples here. The public school enrollment of Akron is approximately 14,300 students. Assuming a decline in enrollment at the rate of 4.5%, what will the enrollment be in 5 years? So in this case, we've got a decline. So y is going to be equal to, our initial amount is 14,300 times e to the r. The rate in this case we need to make negative because it's a decline, and it's going to be 0.045 times the number of years in this case is 5. So again, if we go to our calculator, we have 14,300 times e to the negative 0.045 times 5. And again, this is all in parentheses, so this is all our exponent. And we end up with 11,419 students approximately. And in this case, we rounded up to 419 students because we don't want to deal with partial students. It's just kind of weird. Anytime we're dealing with people, we usually round up to the nearest person. I want you to pause the video here and now try the next example, then resume the video to see if you've got the correct answer. So for this example, you should have ended up with about 5,638. Again, we rounded up to the nearest whole bacteria because we don't want to deal with partial bacteria. Okay, we've got one more example here. A model for the number of people on a college campus who have heard a certain rumor, so this is the model for how rumors spread, is n equals p times the quantity 1 minus e to the negative 0.15 d, where p is the total population, d is the number of days that have elapsed since the rumor began, And again, this was all a matter of before social media, so things spread a bit faster since this model was created. UA has approximately 28,000 students. Suppose a rumor is started regarding an increase in tuition. How many will have heard the rumor after 4 days? So all we're going to do here is plug in the D, which was 4 days, and the principal, the initial amount, which was 28,000. So in this case, N is going to be equal to 28,000 times the quantity, 1 minus E to the negative 0.15 times 4. And again, we've got to be very careful about putting this in our calculator to make sure to include parentheses. So we're going to have 28,000 times parentheses 1 minus e to the negative 0.15 times 4. So we close both of those sets of parentheses and hit enter, and after 4 days, about 12,633 students will have heard the rumor. This concludes this video. There will be a short video that talks about logarithms with other bases, so please make sure to watch that, and when you're done, complete the homework for this section.